Okay, well, today, hopefully, we're going to look at Model Sim. Um, I should have tested this ahead of time, I guess. My Model Sim I've used for 2 years quit working. Um, Tells me I need to go up to get an updated copy of it. So I thought, well, I'll just do this on this so you can see how to install it. Okay, so I went to the model.com or whatever the website was they said, and click through, and I'm at mentor.com/company/hire_ed/model sim-student-edition, and I'm at here to download student edition, and hopefully it doesn't make me verify before it'll download. 6204416 6559 College. Yeah. Let's see, 2205 shorts. 67152. Okay. In the past, I never asked you to check your email to verify it or anything. So basically, don't do it for commercial purposes. It's got limitations on it anyway. I agree with this. Okay. Um, and the okay. Now I signed in my email. I paused it, and here it says download latest Model Sim PE Student Edition. It's downloading. Guess I should have ran on assumption that my software would run forever. I guess while that's downloading, I could start talking about. Let's see here. Okay. Design encapsulation modeling with HDLs. Actually, let's start running. Back up to HDL languages. Hardware description languages, HDL. Hardware description language is a computer-based language that describes the hardware of a digital system in textual format. They talk about the history here and so forth. HDL is a modeling language rather than a computational language. So you're not going to see your typical for loop and while loop and so forth. An HDL resembles an ordinary programming language such as C, but is specifically oriented at describing hardware structures and the behavior of logic circuits. It can be used to represent logic diagrams, truth tables, Boolean expressions, complex abstractions of behavior of the digital systems. Um, timing verification. We're going to see all that. Did I plug in my? Yeah, I did. Okay. Companies that design integrated circuits use proprietary and public HDLs. In the public domain, the IEEE supports the following standardized HDLs: VHDL, Verilog, and System Verilog. VHDL is a U.S. Department of Defense mandated language. The path of development of Verilog ultimately led to its being a proprietary HDL of Cadence Design Systems, which transferred control of Verilog to a consortium of companies and universities known as Open Verilog International. As a step leading to its adoption as IEEE standard. Okay. Verilog design encapsulation. They talk a little bit about examples there of keywords, what a module is, and down to our first example, Verilog. Okay, so if I'm trying to write this in that language, we got our OR here, and that's going to give us, and you see this D here, we haven't seen that before. That's because in programming these, you have to put it into an intermediate location, and then have a transfer on. So you can't have a transfer directly. And then C's coming into that, so we're going to take D and C, and that's going to give us E. Now notice everything has labels here, even our output, because when we program it, we have to handle that. And I think I got done downloading. Did I not click it? It's on a different page. Okay, so let me double click that. Yes, to install. That's a bigger issue if I'm running out of disk space. That's interesting. Free space, 539 gigabyte. Not sure why I gave you that error. Maybe it's because it's their student edition. Now these people are in the business, so they. I'm sure their professional version you buy for design in real life. They put more effort into it. Okay. Just in case that takes a while, let's go over and talk more about that program. Okay, now up here you got your module name, and that can be whatever you want to call it, but the module has to be that module, all lowercase. The or underscore and can be whatever you want to call it, and you notice we have a beginning parentheses, and then we define our outputs and inputs. Output first, this is our ending that's going to come out, and then our inputs, those are going to be what's coming in over here, so A, B, C, and then you do a closing parentheses and then a semicolon. I almost think of those like parameters and so forth. What's coming in, what's going out. And I think of this like a variable, even though it's not. We specify a wire. This is where we're going to have an intermediate result. And notice it ends with semicolon. And then I assign D equals, and A, and then the two pipe symbols is the OR. So that's our A or B, as you see right here. And I'm assigning it to D. And then I'm assigned in the E, the result of this, which is D and C. Notice the two ampersands, two and symbols. That's a logical and. And then these are just comments, so you can put anything here or leave it off. And then our in module ends the module. So it's not hard to design that, the very basic ones. Would you like to modify to your path? This is used for combining both compiles and simulations from DOS boxes. I'm going to do DOS boxes. Somebody no. Must first submit a request for a free license. Okay. And have one email to me. David.hayes@cali.edu 620-441-6559. David.hayes@cali.edu 2205 shirts. Jordan Loop. Wellington, Kansas 67152. College instructor. Student. Used or are using CBHTL, the simulation using for educational purposes. Question is if it'll send it right away or. Did I click it? See any errors? Maybe I got to put this in. It's a poor website that. Well, asterisk. Let's fill in all the asterisks. 2020 fall. Asterisks oftentimes indicate you got to fill in those blanks. That's interesting. Go over to Google Chrome. Try it here. Uh, 620-441-6559. Cali.edu. Address 2205 shirts. Jordan Loop. Wellington, Kansas 67152. College instructor. I shouldn't have to do that if I'm not a student. Tools to be used, none. Educational purpose. Okay. Well, we'll see if that comes up while we're online. But this is what you'd have to do to request license and so forth. I've already installed that the newest version, so that's not a big issue. I wonder if it'll come up. That license. I guess don't do it in IE. Where's Model Sim? Hmm. Let's see here. Compile all. Compile was successful. Okay, well, probably not gonna be able to show that, but anyway, I'll show you how to write programs, just not how to simulate it yet. Okay. Okay, so we got that. Let's say I wanted to do this. The exclamation is let me just program something. Okay, so I want to program in a plus b um, a plus b and then plus c times d, something like that. Okay, and how you would do it is if you did a file new project, and I'll go ahead and close that and give it a project name, test. New project, test 10/14/2020. This is a create new file here. Create new file. And it'll ask me what type. So if I'm doing Verilog, I choose Verilog. If I'm doing one of the other ones, I choose that. Test test October.b. Click OK. And you can close that. You can also right click on this and say add to project, new file. But if I double click that, that'll bring my code window up over here. And we got this. I'll go ahead and cheat and copy that from my previous code and paste that in. And okay. Got excited. I heard the email and I thought maybe my license would come in. So module test. Now we're gonna have our input come in. So our input was A, B, C, D. A, B, C, D. Now for this one, we had a wire here of D. So that's kind of our intermediate. That's not the same as like the inputs and outputs. So keep that in mind. So for this one here, I'm going to have A, B, C, D come in, and I will need an output. And I'm only going to have one output. So E is fine as anything. Down here, for my wire, let's start with just one of them, F. And F is going to be this A plus B here. Keep in mind what the plus represents. So F is going to equal to A and then plus, and that's the and. And is multiplication. Okay, so that'd be the or. B, like that. And then I need a G. That would be these two, C and D. So C and D. Then I'm going to take the F and G that this represents and do a plus between them. And that's going to give me my output. So sine E equals to F. There's a plus. So that'd be my or G. That would be the implementation of this right here. Okay. Let's go back to the book. They talk about identifiers and so forth. I'll let you read that. Talks about the A, B, C, D, and E are Boolean variables because we're talking about circuit. You know, voltage coming through ones or zeros. Continuous assignment is specified by the keyword assign. The assignment is continuous in the sense that it always, for the duration of a simulation, governs the relationship between D and A and B. The two and symbols, that's easy. The or is the two pipe symbols, not so easy to remember. And the exclamation, if you've done any programming, is a not. That'll make perfect sense. These other ones do too. If you're programming in C, the pipe symbol and the ands, ones in the exclamation are what you're used to seeing. Keywords are not logic gates, but a synthesis tool may associate gates with them. Okay, this talks about the ports of the inputs A, B, C, and output E. If I was trying to do this one, notice you have A, and they're doing it all in one line, and you can do that. You don't have to have it on separate ones like I was showing. I did this, but I could have simply said sine E equals to A or B, and then or, and then C and D. Then we had A coming in, and then we had an inverter here. That's the exclamation A we see right here. Then it's coming into an OR gate here. That's this right here. So that's the OR. So I got not A or B, as you can see from there. Then there's a little circle in the front. The little circle in the front is accomplished by putting a exclamation in front. Now, when you put an exclamation not in front, which I quit popping up, then you have to have a parentheses around all that to say I'm inverting all of it, and that accomplishes that little circle. Then that is going into D, which they don't have specified here. kind of did that wrong. That's okay though, because they're telling you. Oh, they're not telling you to. Well, they tell you to use D as a Boolean variable, but they don't use D at all in their answer. Technically, if I wanted to program that, okay, so we're going to have 3 inputs, A, B, C. You could have output. I'll just leave that as E. Wire, they want a D in the middle. And then I'm going to have not A and B come into it. So not A first. That's a not A. And B. So and, or that's an or. Wait a minute. That's a or. So pipe symbol. And then B. Now with the invert there, I want to put parentheses around that in that manner. So not A or B, or not A and plus B. Then I have this inverter on the front, which means I need to put an exclamation in the front, but then I have to put parentheses around all this, as I indicated earlier, and that'd be my D. So then, Y would be my output. So Y is equal to, take the result of D and C, and I got an and between them. So C and D. And that'd be my my program. It's different type of language. Okay. I guess they just left a lot out. Because all they're asking for is a statement. Okay. So let's, without looking at it, let's program this. Okay, so I'm going to have inputs is A, B, C, D. That. And I heard my little email thing going. No license. Okay, an output. I'm pretty sure you can have 2 outputs. Let's see if that's true statement. Yeah, 2 outputs. Okay. Try and do that without looking. Except for I did look. Okay, so outputs E and F. Now this first one, and I could do this all in one line if I wanted to, or have separate wires. Doesn't say anything about separate wires. So sign, get rid of that wire. E equals A plus, which is an or, B and C, so put parentheses around it, B and C plus not B and D. Now I need parentheses around that. So that should accomplish it. And for F, sine F equals to That's not B, not B. There's an and between them. So and C, closing parentheses on that, and then there's a plus between them, so that's an or. Beginning parentheses, and then B, and it looks like C prime, not C, and D prime, so not D. Let's see how that compares to what they got. Input, output, okay. Wire rich. They got an error, but I'm not sure where the error is at. Guess I could bring up some of my previous code and look at it. Okay, save that. Okay. It's curious. I wish I wouldn't have errors in the book. It's disturbing. Unless it doesn't matter. You see how this is a comma here after the output? And you can have those input and outputs reversed, by the way. But then all of a sudden they change to a semicolon. And I wish I could test this theory, but I think it should be a comma instead of a semicolon. Once we receive the licensing for that, then we can actually check that, but that's what I believe it to be. Maybe it doesn't matter. Maybe it could be a comma or a semicolon. Typically, up there, your semicolons at the very end like that. Actually, I guess I could test that because I can compile it. Let's put a semicolon there. Save that, and then I'll do a compile all. Yeah, I thought they had an error. Assuming that's the error. Okay, so let me come up here and put a comma there. Might have to save it first. Save it. See, and it compiled fine. So it should be a comma. I don't know why they put programs in here they don't actually test. But anyway, regardless, you'll find some of these codes don't work, and you're sitting there. That's nice. Now they did this one a little bit differently. Notice here they specified parameters here. This would be so you can call this somewhere else, and we'll see that with later on. But see if they talk about that. So I don't even think you can put a semicolon here. I think it'll give you an error. Got to remember to save it though. I remember that from before. Yeah, I didn't like a semicolon there. Okay. Again, the whole idea of a module is something you can run. So you could build this. Have a bunch of different modules that do different things. And the module name should tell you what it's going to do. This tells you it's going to do an OR and then an AND. Okay. Now this was up here. Was Verilog. Down in VHDL, design encapsulation. Design encapsulation in VHDL has two parts, an entity and an architecture. VHDL entity, number one, provides a name by which the design can be identified, and two, specifies the interface of the design with its environment. The name and direction of each interface signal and its data type are declared in the port of the entity, and the syntax is given below. The simple example is given by this. So a simple example is in the specifier port, out, Y out, and X in. Signals may be declared in the port. I'll let you read more about that. I'm not a big fan of VHDL. Over here, if you right click and choose add to project, new file, you see VHDL is one of our types. So different way of specifying the same item. I'm going to focus on the Verilog just for interest of time. I guess I like Verilog because it's more programming based, seems like to me. But if you're going to go into designing a circuit, you probably should be good with both of them. That's why I'm going to leave that with you to explore. Verilog has a family of built-in structural objects called primitives that enable direct modeling of combinational logic. For our purposes, the most important keyword names of Verilog primitives are AND, NAND, OR, NOR, XOR, XNOR, buff, not, buff if 0, buff if 1, not if 0, not notify, and not if 1. And then you go through and describe them, though you can probably guess. This is so you don't have to put everything in terms of ands and ors. Specifically, remember some of our design, we needed to have nands and nors versus something else. So. part of programming this is you'll have to consider a time element. Let's see. Structural model of the circuit in figure 3.37 and or propagation delay is specified by a list of defined primitive gates, each identified by a scripted keyword. Circuit has one internal connection between gates G1 and G3. The gates are connected by W1, which is declared with a keyword wire. Elements of the list are referred to as instantiations of a gate, each of which is referred to as a gate instance or primitive instance. Each gate instance consists of a primitive name, an optional instance name, such as G1, G2, and so on, followed by a list of common separated gate output, input. Rule language is that the output of a primitive gate must be listed first, followed by the inputs. I thought you could reverse those, but that's indicating it should be in that form. Rule language is that the output of a primitive gate must be listed first in the inputs. For example, the OR gate in the schematics presented by the OR has instance name G3 and output D and inputs W1 and E. Although the output of it must be listed first, the inputs and outputs of a module may be listed in any order. Okay, that's what I'm thinking of. Here's where we put our delays in. So you see the pound 30, pound 10, and so forth. The idea is you're trying to get them to arrive at the same time. And so you have to put a kind of a delay in there of some sort. I'm not sure if I understand this delay exactly. I know what they're trying to accomplish here, but I'm not sure why this is 10 nanoseconds. It's almost like they need to slow this down. Besides doing the invert on it, they need to slow it down before it gets to this gate, so that I would think, in theory, that this would arrive at the same time as this. But if this is waiting 30 and this is waiting 10, C is still going to arrive first. But regardless, maybe they don't mean anything by that example. Maybe they're just showing you. Okay. Gate delays. All physical circuits exhibit a propagation delay between transition of input and resulting transition of output. When an HDL model of a circuit is simulated, it's sometimes necessary to specify the amount of delay from the input to the output of its gate. In Verilog, the propagation delay of a gate specified in terms of time units by the symbol £. Number associated time delays in Verilog are dimensionless. The dimension of I guess it's not nanoseconds. The association of a time unit with physical time is made with a time scale compiler derivative. This is where you tell it right here. First number specifies the unit of measurement for the time delays. Second number specifies the precision for which delays are rounded off. In this case, 0.1. If no time scale is specified, a simulator may display dimensionless values or default to a certain time unit. That sure looks like 1 nanosecond is 10 to the negative 9 seconds. Our examples use only the default time unit. How's that work? Well, you got your inputs coming in, and they're going to change based upon what's being done here, from your gates and so forth. Let's see. Okay, so let's bring in the code. There we go. Okay, so we have our E, which is over here. We have our W1, which is right here. And we have our D, which is right here. Then we have our input. So initially there's no input. The zero's coming in here. And if I follow this logic, let's see, 0 and 0 is 0, so that's bringing a 0 in here. C is coming in as 0. This is inverting it to a 1, so that's coming in here. So this would be 0 or 1, which is 1. That's why D is 1. W1 is 0 because 0 and 0 is 0. And E, C is coming in as 0. That inverts it, so it comes in as 1. So that explains that first row. Now I change it for some reason. I turn on the voltage and all these coming through. Well, since there's propagation delays in here, my E, W1, and D are still 101. Hadn't taken effect yet. Okay. And by the way, you notice in all these the inputs didn't change because we're just taking a look at the flow through it. After 10, I'm gonna say nanoseconds. I'm pretty sure that's nanoseconds. But after 10 nanoseconds, the C has changed. Not the actual C, but the voltage coming through. So it changes to a 1. And now you notice that E, wait a minute. No, it comes in as a 1. So this flips it to a 0. The E has now changed to a 0. Let me actually write that. I think I got a tab in here. I'm running out of time. It's important to understand those delays. Okay. So again, after 10 ns, the 1 is flipped to a 0, and that just comes straight through the E. And so you notice the E has now changed to a 0. It was a 1. In addition to that, that 0 is coming up to here. Now notice that W1 hasn't changed because there's a 30 NS here. So W1 hasn't changed. Notice also the D has not changed. So because there's a delay here. This part that'll throw me a little bit. Okay, so that's after 10. After 20, you notice that E shouldn't change from here on out. So I won't even mention it anymore. See how E is zeros all the way down? Because it's just a straight pass through here. So that means that once that gets changed, then that doesn't get affected. But notice that W1 is still 0. So that's still 0, which it should be, because this is waiting 30 total. And notice that D is equal to 1. Okay, so then after 30, again, E never changes. And W1 is now changed. W1 is now a 1 because 30 NS has passed. So it's passing through A and B. So then that's going to affect this right here. And 1 and 1 gives me 1. So that's why this changes to a 1. Okay, now D has changed. And D is now 0. Reason why is because W1 initially was 0. This waited 10 NS before it passed through here. And then it's sitting here with the old value of W1, which was 0, and doing 0 or 0, which gives you 0. Now, let me think about that. Okay, 10 D. Okay, yeah, that makes it 0. I'm thinking of the value here coming in here. I can't be thinking along those lines. This is working off the old, so that's passed through. Because it's 10, 20, and it's gone. But so by the time that this gets there, this is already passed through because this is 10 plus 20, and it's already passed through. Then this has now arrived, and this is now 1. But it's got to wait another 20 NSs. So you see that D doesn't change after the first 10 because it just won't. And then after the next one, it's now waited 20 nanoseconds or NS, and now it has changed because at this point, you know, this arrived, and this is still 0. That doesn't change, and then it passes that through, and 1 or 0 gives you 1. Remember how I said this didn't make any sense because this would arrive first? Yeah. Yeah, almost think of like you're going to a movie theater. You know, this person's this person arrives after 10 minutes. They go ahead and go into the movie theater, so they're being processed. This person comes in 30 minutes after 30 minutes, so they arrive in late. So when you're designing a circuit, you have to plan your timing on that. Okay. Yeah. Next time we'll talk about this test bench right here for. It's a test bench is a way for you to test your code. Okay, yeah, we'll go ahead and stop there. And hopefully I have a license for that. I mean, we can still compile it, make sure our code is right, but the simulation helps show the change in some of the voltage. So